One of the major concepts we looked at in the beginning of this unit was specific heat capacity, which involves the heat transfer and energy changes when we are in a single phase of matter. For example, the energy that would be involved in heating up some liquid water. Phase changes will involve a different type of energy transfer. During a phase change, all of the energy input goes into actually changing the phase. The temperature does not change. In other words, if I have a sample of ice at 0 degrees Celsius and I input energy, the temperature of that will not change until all of that ice has melted into liquid water. And so when we're investigating the energy changes involved in these phase changes, we look at something that we call either the heat of fusion, if we're looking at our melting or freezing points, or the heat of vaporization, if we're looking at the energy involved in either vaporizing or condensing. And we denote these as a delta H of fusion, FUS, or delta H of vaporization, VAP. And so again, what we have is a difference in what the energy does if we are changing phases or if we are heating a substance up. In the case of a phase change, so here we would have just a sample of ice, so pure frozen water. We input 500 kilojoules, and we see that now we have some liquid and some solid still, but the temperature has not changed. And so during phase changes, again, the phase changes, we start to get some liquid, but our temperature stays the same. This is different from just heating something up when the phase does not change. In this case, we have a sample of pure iron, and we heat it up, and our molecules definitely start to move faster, but we remain in the solid phase. So the energy does not go into a phase change. Instead, it goes into raising the temperature of the substance. And so during phase changes, no temperature change. When the phase is not changing, inputting energy does change the temperature, but the state does not change. And so here we're going to take a look at what we call a warming curve. In this case, we're starting with a sample of pure ice, and so frozen water at minus 50 degrees Celsius, and we're going to heat it up until we eventually have water vapor, steam, at 200 degrees Celsius. And so we can see here that first starting at a temperature of negative 50 degrees Celsius, the energy that we are putting into this system is raising the temperature until we reach the melting point at 0 degrees C. At that point, all of the energy that we put into this goes into actually melting our sample. Our temperature does not change. And so at this point in the curve, we have pure solid, and then we're melting until we get to pure liquid. At the point we have a pure liquid, now the energy will once again go into raising the temperature of that liquid until we get to the boiling point of 100 degrees C. And so here, we're still at pure liquid at 100 degrees Celsius, but now all of the energy will go into breaking up the forces that hold the liquid molecules together until finally we are now at 100% steam. And then once again the energy will start to raise the temperature of that steam. And so if we wanted to calculate the amount of heat that would be absorbed as 500 grams of water is warmed up from negative 50 to 200, then we have 5 different steps in that calculation. We have to first look at the energy required to warm the ice to the 0 degrees Celsius. Then we look at the energy required to melt that ice. And then the energy to take that liquid water up to 100 degrees C. The energy then required to evaporate and to transform all of that liquid water to steam. And then finally, the energy required to heat that steam up to 200 degrees Celsius. And then we can simply add up all those different energies to get the final energy required to raise the water from -50 to 200 degrees C. And so remember that when we're looking at changes of state, the energy transferred as heat in order to convert a substance from a solid to a liquid is called the heat of fusion, whereas the energy required to convert from a liquid to a gas is called the heat of vaporization. And here we have just a few examples of some common substances and their heats of fusion and heats of vaporization. Let's look at a couple simple examples of how we use these. Here, we want to calculate how much energy it takes to melt 27.3 grams of aluminum, which is already at its melting point. And so remember that since we don't have a temperature change involved during melting, our heat is not going to take the temperature change into account. And so the heat required in order to melt this is going to just depend on the mass times our delta H of fusion. And so in this case, our mass, 27.3 grams, times our delta H of fusion of 395 joules per gram, or 10,783 joules, or 10.8 kilojoules. Here, we're looking at how much energy it takes to vaporize 310.7 grams of water, which is already at 100 degrees C. Same exact idea. Our heat is going to equal our mass times our delta H of vaporization. So we have our mass of 310.7 grams times our delta H of vaporization of 2260 joules per gram, which is going to equal 702.182 joules, or 702.2 kilojoules. Now let's put this all together into one big warming curve for a substance. And so again, what we want to do is use our values for all of the different changes and then add up those values for the total energy change. And so in this example, we want to calculate how much energy is going to be required in order to heat up 150 grams of solid water from -45 degrees C to steam, water vapor, at 255 degrees C. And so we have 5 distinct points on this curve. We first have AB, in which we are warming up our sample of ice. And so since we're warming up, AB is going to be Q equals MC delta T. And then, along the BC line in our curve, we are now melting the water. And so we're going to use our heat of fusion, where Q will simply equal our mass times our heat of fusion. Along line CD, now we are once again warming liquid water, and so that will be Q equals MC delta T. And then we are once again at a point where our temperature does not change while it is converting over to water vapor. So along line DE, we're going to use our heat of vaporization times our mass. And finally, along line EF, we are now warming up our water vapor. And so that will be Q equals MC delta T. And so let's calculate all of those. And so along the line at AB, we said we're warming the ice, so that is going to be Q equals mc delta T. Our mass of the ice is 150 grams. Our specific heat of solid water is not the same as liquid. We look up our specific heat of solid water, we get 2.108 joules per gram degree C. And our temperature change is going from 45.0 to 0. So a temperature change of 45.0 degrees C. We add those up and we get a Q for this phase of 14,229 joules. You'll note at this point that I am keeping all of those numbers. I am not rounding for significant digits. I'll do that at the end for the final calculation. Now we'll calculate the heat associated with melting the water along the BC portion of our curve. We said that here we're just melting, and so our Q will be equal to our mass times delta H of fusion. So that will equal 150 grams times the delta H of fusion of water. It's 333 joules per gram. And so it will take 49,950 joules in order to melt this ice. Now that the ice is melted, we can calculate the amount of energy that will be required in order to raise the temperature of that liquid water up to the boiling point. And so now we are changing temperature of liquid water, and so that's going to be Q equals mc delta T. Our mass of 150 grams times the specific heat of water, 4.184 joules per gram degree C. We're going from 0 degrees C to 100 degrees C, the boiling point of water. So that's a temperature change of 100 degrees Celsius for an energy requirement of 62,760 joules in order to raise the temperature of this water from 0 degrees C to 100 degrees C. Now that we are at 100 degrees C at the boiling point, along line DE in the curve, we are just changing phase from liquid over to a vapor, and so our Q is going to be equal to our mass times our delta H of vaporization. So a mass of 150.0 grams times the delta H of vaporization of water of 2260 joules per gram for 339,000 joules in order to vaporize this sample of water. Finally, now that all of the water is in the vapor form, we can calculate the energy required in order to raise the temperature of that vapor from 100 degrees C to 255 degrees C. And so EF in our plot, since we're raising our temperature now, the heat will be equal to mc delta T, our mass of 150 grams. The specific heat of steam is 1.996 joules per gram degree C, times the temperature change of 155 degrees C. And so it will take 46,407 joules in order to raise the temperature of the steam from 100 degrees C to 255 degrees C. And so, in order to calculate the total amount of heat involved here, our Q total will just equal the sum of all of the different heats that we just calculated. And then we can add those up for a total amount of energy of 512, 346 joules, or 500 kilojoules of energy in order to convert 150 grams of water at minus 45 degrees C into steam at 255 degrees C. And so our big takeaways when looking at phase changes is that as we are changing phase, as we are going from solid to a liquid or liquid to a gas, or in the other direction, if we're going from gas to a liquid or liquid to a solid, our temperature does not change while that process is occurring. And so we no longer use the specific heat to calculate the energy of those processes, but we use the delta H of fusion when we're looking either at freezing or melting, and we'll use the delta H of vaporization when we're looking at vaporization or condensation. And remember that since the temperature does not change, temperature does not show up in our equations. And so we would have the heat associated, for instance, with melting would simply be equal to our mass times our delta H of fusion. Whereas our heat associated with vaporization would be equal to our mass times our delta H of vaporization. I hope this video has been helpful. For more assistance, please feel free to look at the website.